Astronomy Department. Today we have the pleasure of receiving remotely Camila Paiva Vice. Camila is a researcher at the Astrophysics Division of INPE. She holds a PhD in astrophysics from INPE, and her research focuses on statistical analysis of cosmological data and simulations, including the CMB, the 21 centimeter signal, and other traces of large-scale structure. So Camila, whenever you're ready, please feel free to start. Thank you.
Thank you, Rubens. Also, I would like to thank Maria Vitória for the invitation. It's a pleasure to be here. Actually, I would like to be in person, but since this time was not possible, I hope to have the opportunity to be there in time at some point. So I am just going to share my screen. Can you see my screen?
Yes.
Yes? Yes. Okay. Any problem, please just let me know. So in this talk, I would like just to tell you about some work that we have been developing at INPE with the cosmology group there. So I will just So I will just start with some aspects of cosmology today. So you can see here in this plot on the left a graph where we can see the energy density of some components of the universe, the radiation in in red, and the matter dominating at some point, and today the cosmological constant dominating. So according to our model, this is the contents of the universe, how the universe, so you can see here that most of our universe, the content of our universe is dark energy, which is represented here by this lambda, this cosmological constant, which in our lambda CDM model is a constant in time. Second is dark matter, and just a small fraction of the visible matter. So we say today that we live in a precision cosmology, that we can do precision cosmology with CMB, for example. We can say this because, as you can see here from this small table, that we can measure most of the basic lambda CDM parameters with less than 1% of uncertainty. So this is why we can say today that we are doing precision cosmology. But of course, we have some problems, but not exactly problems, because we are always discovering new things. And one new thing that we discovered last year with DESI, with the release of the first results of DESI, is that maybe our universe is not being driven by a constant, cosmological constant, but maybe a dynamical dark energy. And this is what these DESI results is telling us with this plot here, where we can see WA and W0. And for the lambda CDM model, we should have here WA is equals to 0. And so these ellipses here is telling us that maybe we don't have a cosmological constant, but dynamical dark energy. So apart from that, we have also what we call the S8 tension. As you can see here, we have some constraints on the sigma 8 parameter, which is a bit different from what we have from estimated using CMB, but with less results of kids. Maybe this is not exactly a tension anymore, but here with the age not tension, this is really a tension today in the cosmological scenario. And this is really something that we have been trying to answer and to understand. So although we can say that we are doing precision cosmology, we have still many questions that we need to solve. And I am mentioning here just a few of them, maybe the most famous. So, but how is it that we are doing this? How is it that we are doing cosmology, and from where in the universe exactly we have been taking data and information so that we can get to this information that I just summarized here for you. So mainly we have been observing the early universe around 400,000 years after what we call the Big Bang. When we observe the CMB, we have many instruments. We have used many instruments to observe CMB, and I put here the three main ones that did a full sky survey of CMB. And we also have many instruments observing the later universe. Here I also include some examples. For example, the DES survey. Currently, we have some results, and we are expecting new results from DESI. And in the future, we will have the LSST survey bringing many information. And of course, we have James Webb Telescope bringing us information from other epochs of the universe, but we still have many gaps in the history of the universe that we still are not able to observe. So maybe, for example, the Hubble tension could be solved if we understand more and if we get more data and observation from these epochs that we, for now, are not able to observe. So, but why is it that we need and we are interested in observing the large-scale structure? Because actually, at the end, what we want to do is to map the distribution of the dark matter. But we cannot see dark matter and we cannot observe it directly. So we use what we call tracers of the large-scale structure of the universe, the tracers of how the dark matter is distributed. So one example is weak lensing, where we take the deviation of the lights of the background galaxies, so that mapping them, we are actually mapping the distribution of the dark matter. Another example is galaxies. We can measure the galaxy clustering, so we can survey galaxies. We can map the position of galaxies so that we are mapping the position, how the dark matter is distributed. And a new, relatively new tracer is the 21 centimeter signal from the neutral hydrogen. And this is a new tracer that I am going to focus in this talk. So, which is the idea with the 21 centimeter signal? I told you 2 slides ago that today we have most of our information to do cosmology is basically coming from the CMB and from later universe with our galaxy surveys. And now with the 21 centimeter signal, we are able to go much further in the history of the universe to get information and help us to do not only cosmology, but also astrophysics. So with 21 centimeter and other lines, other emission lines, we are able to observe all these epochs inside of this red rectangle. So from this epoch, the so-called the Dark Ages, we will not be able to observe it from Earth, for example, with using the 21 centimeter line, because we are not able to observe the very small frequencies. So to do this, we would need to take our radio telescopes and put it in the backside of the moon to be able to observe these short frequencies. But since starting on the beginning of the reionization, we would be able to use this signal to observe the universe. So in this epoch, when the reionization is happening, we would see this 21 centimeter signal as huge bubbles. And as soon as this reionization finishes, most of the neutral hydrogen in the universe will be concentrated inside of galaxies. So it means that when we observe the 21 centimeter signal, we are basically observing how the galaxies are distributed in the universe. And here I put a few examples of radio instruments in construction, already observing. So for example, Meerkat is already taking data with many results and some data released. SKA is for the future, and here I put other examples, for example, Shime, Lofar, Hirax, Tianlai, and also Bingo, which is a telescope being constructed in Paiva. So which is the idea of using 21 centimeter signal to map our universe? So in the same way that we can point our telescope and to the galaxies and map the position of the galaxies using the optical instruments, in the same way that we do, actually not exactly in the same way, but similarly as we do it with optical telescopes, we can use the 21 centimeter coming from galaxies to do a kind of survey of galaxies using the 21 centimeter signal. But the problem is that the 21 centimeter signal is super, super faint. So to do this in the way that we do with optical surveys, it would be really, really expensive, and it also requires too much sensitivity to be competitive with optical surveys. So this type of survey using 21 centimeter signal is quite impossible to do, to go at high redshifts, but not if we use the same signal, the same 21 centimeter signal, to do actually not a galaxy survey, but an intensity mapping. So you can compare this with, for example, CMB. So instead of trying to find the position of the galaxies, we are basically pointing the telescope to the sky and measuring all the photons arriving in a given bandwidth. And what we are measuring is actually temperature fluctuations in each direction of the sky. So we have here an example of temperature fluctuations from intensity mapping. And what we measure at the end is not the position, but some kind of diffuse signal. And we use for this, in this case specifically, I'm using the example of a single dish mode. So we have here a beam. So actually in this way, we are able to map mainly the large scales, but not the smallest scales as we can do with galaxy surveys, where we can find the position in the sky of each galaxy. But this can bring us many, many information on cosmology using the large scales. So which is the idea? I'll put this video here because I think it helps us to understand. So as I told you, most of the neutral hydrogen are inside of galaxies. So we basically, when we observe the signal, when we measure the signal, we are measuring the signal coming from the galaxies. And when we measure it here with our instruments, we are actually measuring a redshifted signal. So when we define the wavelength, the frequency at which we are going to observe, we automatically are defining the redshift beam at which we are going to survey the universe. So basically, we are slicing our universe, observing beams of redshift or beams of frequency, which are directly related. So this is why we also say that we are kind of doing spectroscopy because of this, because we have a very precise measurement of redshifts. So the interesting thing here is that, as I told you, we are going to trace the large scale structure of the universe, so we can do many cosmology by doing this, but we can also constrain, for example, the H1, the neutral hydrogen evolution in the universe, and the evolution of galaxies. Because we are doing this, we will be able to trace how this H1 is evolving with the redshift. So as I told you, we can do both cosmology and astrophysics. So, and also I told you about this large scale. This is a plot of what we call power spectrum. I will talk a bit about what is this power spectrum. So this is a kind of measurement of how clustered are the galaxies here, in particular, how clustered are the signal of the 21 centimeter intensity mapping. So we have measurements using a cross correlation between Mirkeles, which is a 21 centimeter telescope, and WIGO-Z, which is galaxy survey, the same for gamma. So we have here measurements of this power spectrum, and we can see here from these equations that we can directly relate the power spectrum measured from the H1 signal to the power spectrum of matter. And we use these parameters to relate the both of the two of them. So here we have the density parameter for the H1 signal, and here the bias parameter. So by measuring this, we can constrain these parameters. So we can measure how the H1 signal, the H1 content of these galaxies are evolving with the redshift. And the same here when we use, because this is actually a plot of the cross correlation between the 21 centimeter signal and galaxies. So we can model the relation of them in a very similar way, but including this bias of the galaxies. The bias is basically a parameter that we use because we don't know exactly how the two of them are related, how exactly our tracer is related to the dark matter. And here I just call the attention that the temperature of the H1 is directly related to the density of this component of the hydrogen. So it means this is why we are actually measuring a temperature fluctuations in the sky. And here we have other examples of how we can do cosmology and also astrophysics. So again, in the astrophysics, I'm showing here a plot with some measurements of this parameter of the H1 with respect to the redshift. And we expect that in the future, we can populate this graph. And also, I can show you here an example of a forecast for SKA, showing that using intensity mapping, we can get closer to the sensitivity, for example, of Euclid. And here in this plot, I am also showing you how we can do, for example, BAO using intensity mapping. So just I would like to do this parenthesis before we continue, is just to remember that in cosmology we are basically doing statistics. We cannot trace back the position of galaxies individually, but we can do statistics. For example, let me put this video because it shows us how what is it that we can in fact predict, which is the 2-point statistics of these observable. So for example, here we have the 2-point statistics, which is basically a counting of pair of galaxies in the sky, and we continue counting it so that at the end we will have what we call the 2-point correlation function. And this is what this is our 2-point statistics. So the final curve is our 2-point function, our 2-point statistics. So when we have these 2-point statistics in real the configuration space, in the real space, which is the one that I just showed you, we can just do, for example, a Legendre transformation so that we go to the harmonic space. And we can also do a Fourier transformation from the real so that we have the P of K, the power spectrum, which I showed you a few slides ago. So this is just for those that are not in the field to understand what exactly are these 2-point statistics. So what is, now back to the 21 centimeter intensity mapping. How is it that we observe it? So we have here the matter distribution, and we have here the 21 centimeter signal, which is related to the matter distribution through a bias that I just commented. And when we look at the sky and measure the signal, we are not able to measure just the signal, but we measure all the signal that is coming to our telescope, which means that we are measuring the cosmological signal, the 21 centimeter signal, all the foregrounds from our galaxy, and also extragalactic foregrounds, plus RFIs, for example, which are another contaminant. And after this, the signal enters in our telescope, which also have this beam effect. Then I am going to talk about it more later. We also have the instrumental noise. So as you can see, our observation is not the observation of the cosmological signal, but it has many other components, and we need to understand all these components so that we get rid of them and get only the 21 centimeter signal. So you can compare this with, for example, what we have for CMB. We have, for example, Planck satellite measuring different frequencies, and we use all these frequencies to clean our data so that at the end we just have one map, one CMB map. So here is similar, but a bit more complicated because instead of having just one CMB in the 21 centimeter, we will have as many 21 centimeter maps as we have of frequency. So for each band, we will have a different 21 centimeter signal. So we have to remove all this contamination, and at the end, we will have one map for each frequency, because we are tracing different volumes of the universe with the different frequencies that we are using. So how is it that we can, for example, mitigate the systematics, mitigate the fact that we have many systematics, many contaminants in the 21 centimeter signal? So one possibility is that we combine it through a cross correlation, for example, with galaxy surveys. So here we have, for example, the characteristics for the 21 centimeter intensity mapping, which is a very good resolution in terms of redshift, but not so good in terms of angular resolution. And on the other hand, we have the galaxy surveys, which sometimes don't have many good redshift resolution, but very good angular resolution, because it discriminates the position of the galaxies. And we also use the fact that the systematics of each of them are not the same, so they don't correlate. So when we take, for example, the two of them and construct this P of K, this power spectrum, cross-correlating them, we can get many information, and we can avoid some of the systematics. So here I am including an example of our work from 22, cross-correlating data from Meerkat and WiggleZ, and they found this more than 7 sigma significance, detecting the 21 centimeter signal through the cross-correlation between the two of them. And also the constraint on the parameters that I told you. So what I would like to talk about now is how we can use this cross-correlation using not only surveys with measurements, with spectroscopic measurements of the redshift, but also photometric instruments. So this work led by Gabriel, a student at INPE that just got his PhD. He led this work investigating how well we could get information, 21 centimeter information, cross-correlating a future photometric survey, which is the LSST. So, which is the main motivation? The point here is that all the results that we have by now, cross-correlating 21 centimeter and galaxy survey, uses spectroscopic instruments, because these instruments, they can obtain the redshift information much more precisely. While with the photometric instruments, we don't have that kind of precision, and this will, of course, degrade our results. But the point is that we have many photometric surveys, and we will have this amazing survey, which is the LSST, and we need to check if by doing this with photometric surveys is really not that good, but we need to know. So the idea here was to test the cross-correlation between these instruments, and using as a case study the bingo instrument, which I mentioned a few slides ago, which is a radio telescope being constructed in Paiva. So you can see here the footprint of each of them. So basically, combining the two of them allows us to use the full region that is going to be observed using the 21 centimeter signal. And as a curiosity, I am including also this plot here, where you can see the photometric beams from LSST, and also the beams, the redshift beams of the 21 centimeter intensity mapping. So you can see that we have a very, very thin redshift beams for 21 centimeter compared to the photometric beams. So the idea here is that we simulate the 21 centimeter signal for all the redshift beams expected to be observed. We include all the contaminants, and we also simulate the corresponding galaxy survey, which means the LSST. So for the 21 centimeter signal, we have before the cross correlation, we need to do this foreground cleaning, which I told you that is similar to what we have with CMB. We have to clean all the contamination before we do cosmology with this data. So after the cleaning, we can do or the autocorrelation, correlating the field with itself, or we can do the cross correlation, correlating the cleaned field with the galaxy surface. So if we take a better look on these results, we will see the following. So we have here the multiple times the angular power spectrum. So this is in harmonic space, and here we have multiples. And so we have here the large scales of the universe and here the small scales. So for the autocorrelation, you can see that when we use a field which is, because even after you clean your data, you still have residual contamination of this component, the astrophysical components, and you also have the white noise. So because of this, since you are using the autocorrelation, this signal will appear in will contaminate your autocorrelation. So you can see here very clearly that this dashed line is showing us a bias introduced by this contaminant, these residual contaminants. On the other hand, on the cross correlation, we don't see this bias introduced on smaller scales because these contaminants from the two instruments, they are not the same, so they don't correlate. So even though we don't have this bias, we will have a larger dispersion of these, as you can see here from these colored regions. So although we don't have bias, we will have a smaller signal to noise when estimating the angular power spectrum. So here we can see the statistical significance of these measurements for this forecast. So here we have the statistical significance with respect to the redshift beam. So this is for the autocorrelation. As you can see here, at some point we will have a high significance. And the other three plots are for the central cross correlation. So the central intensity mapping redshift beam with the full photometric beam. So you have here, each of these dots corresponds to the statistical significance for each of the redshift beams. Some of them you can see that we will not have any significance. So we will have more significance for the cross correlation between the central beams with the redshift beams of the 21 centimeter signal around the center of the galaxy, of the photometric redshift beam. So the same here for the other two examples. Here for the second photometric beam, so we are talking about this cross correlation around here in the middle, and here we are talking about this last redshift beam for the 21 centimeter signal. So you can see that because of the large photometric errors, we will have the statistical significance for the cross correlation very similar to what we would have using the autocorrelation in this case. And here we have the forecast that we did regarding the parameter constraints. The parameter constraints here, I mean how well we can constrain the bias and also the density parameter of the neutral hydrogen. In this plot with the autocorrelation, and in this other plot here with the cross correlation. We only have these few points for the cross correlation because we can only do this cross correlation with the redshift beams from 21 centimeter around the center of the photometric redshift beam. So this is the reason why we only have this. So although we don't have this biased measurement of these parameters, for example, here, that we have for the autocorrelation. So you see that we clearly have this bias here, while for the cross correlation we don't have it, because this what is causing this is this residual contamination, and since here they don't correlate, we don't have this bias. But although we don't have the bias, we have larger error bars for these parameters. So just as a conclusion here, the idea is that in fact the photometric errors, they impact in the results, in the parameter constraints, and introduces this kind of bias. But as our conclusion was that still it is worthy to try and to test future photometric experiments, because since we will have many data, and since also our simulations here was kind of simple simulations, we think that when we include more systematics and other and make it more realistic, we will probably have this autocorrelation getting worse, while the cross correlation might continue in this way. Okay, so another thing that I would like to talk about very quickly in my last minutes is about another line of research that we have been doing at INPE, which is trying to answer the following question. Is it possible to use the 21 centimeter intensity mapping to investigate the cosmological principle? Because we assume in our lambda CDM model that the universe is homogeneous and isotropic, and we have been using current data to investigate this. Basically, we use this fractal correlation dimension, which has this aspect here. So basically what this statistics is telling us is that for small scales, smaller than 100 megaparsecs, for example, we don't have this homogeneity. So we have a kind of transition scale to homogeneity when this curve gets closer and closer to 3. So it is defined as when you have this transition, you can say that your universe is homogeneous. So we can do this also on projected data, where you would get this transition scale as an angle in the sky. So how is it that we calculate this fractal correlation dimension? So we start with these counts in spheres, which is basically counting the number of galaxies inside of a given radius. And we do this like by doing a scan of all the sky that you have. And you compare, you divide this by the same number calculated from a random distribution, for example, where you are sure that it is homogeneous. So by doing this, I'm not going to go to the details because I don't have time, but at the end, you can write your fractal correlation dimension as a function of these counts in spheres. And this is the quantity that you are going to measure from galaxy surveys. And now we are showing how we can do it with the 21 centimeter intensity mapping. So the idea here is to calculate this quantity using this 2-point correlation function, because we can, instead of doing this, instead of counting, calculating this count on spheres, in spheres, we can write the same quantity as a function of the 2-point correlation function, which makes it easier for us to calculate. So can we test this with 21 centimeter intensity mapping? We have to remember that we have a beam effect acting here. So this is also similar to what we have for CMB. So this, I compare this with a person that uses glasses like me. So if I take out my glasses, I would see the sky like this. And with my glasses, I can see the sky like this. So depending on the resolution of your instrument, your signal, your temperature fluctuations will be observed like this or like this. So the question here is, which is the angular scale, which is the resolution of the instrument, which would allow us to measure a given scale in the sky. Which scale? I am talking about this homogeneity scale, this transition to homogeneity in the sky. So what happened? This work was led by Bruno, also a PhD student at INPE. So here in this plot, you can see what happens with the two-point correlation function, which is calculated in a similar way as I showed you in that movie that I showed you before. So you can see here what happened with the correlation function, which is this dashed line. So what happens with it when we start increasing this width of the beam, which means when we start degrading the resolution of our instrument. So we see that at some point, at a given sigma max, we will basically erase, for example, the BAO peak. And we are also erasing here the clustering at the smaller scales. So using these measurements of the two-point correlation function, we can use it to calculate this quantity and use this quantity to calculate these D2 statistics that we need to get our transition scale to homogeneity. So what we show in this work is that there is a maximum. So for example, this plot is for a specific redshift. So there is a maximum resolution, a maximum full width of half maximum of our instrument that we can have, so that we still can find a transition scale to homogeneity. If we use full width half maximum or standard deviation of our Gaussian, which is being used to smooth our data. So if we have something, a value higher than this sigma max, we will not be able to measure this transition scale to homogeneity. So this plot is telling us what happens, which is the behavior of this sigma max with redshift. So what we did was calculate this sigma max for many redshifts. So this one is for redshift 0.8. So we repeat this for many redshifts so that we can have this black line here. So this solid line is telling us which is the maximum sigma, the maximum value for the full width half maximum of my instrument, so that I can still measure the transition scale. And this solid line, it is telling me which is where is the division between an inaccessible region, so that for sigma values larger than this, we are not going to be able to measure the transition scale, and while for smaller values, we would be able to measure this parameter. So each of these lines are plotted here for different instruments. So you can see here that most of the instruments that we have here, we would be able to measure this transition scale to homogeneity. And only for these two instruments, which means ASCAP and Meerkat, we would be able to measure this transition scale only in using a given some of the observations, only those with a smaller full width half maximum. So, okay, since I am extrapolating totally my time, I will just skip few slides with another work that we have been doing. And I am just going to mention it very quickly. Because this is something that we have been putting a lot of effort, which is instead of pursuing the traditional way of doing cosmology, like using MCMC and Bayesian analysis, we are trying to use what we call simulation-based inference, which avoids, for example, constructing a likelihood and calculating your covariance matrix, which are things very difficult to do. So we show in this work here that we can do the same thing for 21 centimeter signal using, for example, a neural network to and many simulations to train your estimator, and with this constrain very well cosmological parameters. So I am just going to skip to my last slide. So as I told you before, we have today precision cosmology when we talk about CMB, but we still have many questions. And I think that 21 centimeter can provide strong information, is a strong tool to bring us many information. But to do this, as I showed you, we have to overcome some challenges, and the main ones are this foreground contamination and many instrumental effects like the effect of the beam. So intensity mapping are taking intensity mapping surveys are taking data. As I told you, we have already some released data. But we still have many challenges because we need to understand all these problems so that we can be prepared for the future. And I think that 21 centimeter intensity mapping are still proving its potential, but it is certainly very nice window into the evolution of the universe. And just to finish, I will leave you with this last slide with merchandising of our workshop on 21 centimeter and other cosmological lines that all of you are more than invited. So thank you very much, and sorry that I am over time. The simulations.
The simulation. Yeah.
Here?
The next one, I guess. No, the
earlier here
yeah,
one?
This one.
Mm-hmm.
So how did you get the simulated data to Bingo? What kind of instrumental response function did you use? And if you could provide more information about the status of Bingo right now, because you know it's a very important Brazilian initiative instrument. So can you tell us, upgrade this information to us? And yeah, how did you get this simulated data, and how you compare with the because the left hand side is real data, right, from LSST, right?
Oh no, not yet. These are kind of expected footprint.
Okay. So can you clarify on these issues and how you guys got the bingo?
Yes, sure. Thank you for
Okay.
the question. Actually, I am not involved with bingo anymore, so I am afraid I cannot give you many details. But for these simulations specifically, we considered like a single dish, which is how bingo is going to observe. So bingo is basically a single dish, which is fixed so that the sky pass in front of it, and it is taking data, and the sky passing in front of it. And so the scanning is like horizontal in the sky, so that you have this is why you have this stripe along the sky in equatorial coordinates. And for the simulations, we use just log normal simulations, which are a more simple kind of simulations. And after simulating the 21 centimeter with Flask code, I don't know if this is familiar for you, but we use this code. And after generating the simulation, we include, for example, synchrotron contamination, free. Dust is not that important, but for completeness, we included also Sunev, Zeldovt, kinetic, and thermal. Besides the white noise, for this work we didn't consider more realistic noise, just the Gaussian one, the white noise. And since this Flask tool, it allows us to create these log normal simulations which are correlated, we can test this correlation between the two instruments. Does this answer your question? If not, just please let me know.
Right, thank you. More questions? I could ask a quick question. I think around slide 29, some of those projects had much higher ranges at higher redshift. I was wondering what instrumental feature sets them apart so much?
Sorry, what instrument?
I mean, the yellow and purple lines, they reach much higher ranges at high redshift. So I was wondering if you could comment what features makes them reach such different ranges?
Yes,
from the
it's
instrumental.
because, for example, this red one, which is coming from FAST, we it will survey the universe up to very high redshift, and with a very high resolution, which means very small full width half maximum, or this sigma of the resolution of your instrument. So then the advantage is that this instrument will have a high resolution. So this is why all the observations in all its redshift range will be inside of this accessible region. While, for example, these two instruments, they for small redshifts, they have a beam with a standard deviation around, let's say, 0.45, while for high redshifts, you have a much larger beam, which means worse angular resolution. So this is why they have part of the observations inside of the accessible region and part of it out of the accessible region.
I see now. Thank you.
Yeah.
Sure.
So Camila, because you mentioned several times, you referred to SKE, right? But at the end of the day, Meerkat and ASCAP are pathfinders of SKE. So why is that they are so so bad, let's say, to do cosmology in 21 centimeters? Is simply by construction, because we can see here that meerkat is not appropriate for assessing the homogeneity, right? What is the essential difference between fast and meerkat, for instance?
Okay, so fast, it has, let me see if I remember. I think fast will get this high resolution because it has a very huge plate. So if you see this equation here, this is the resolution and the relation between the resolution of the instrument and the size of the plate of the radio telescope. So if you have very large plates, so you would have a very high resolution, which means is small sigma or small full width half maximum. So as far as I remember, fast is the one with a very large plate, a very large dish, while meerkat meerkat doesn't have this large plate.
But it has several, right? Several that
Yes.
make the interferometry, the effective size of the dish, very large, meerkat. Isn't that so? So why is that?
Yes, exactly. But the point here is that we are considering meerkat here as a combination of many single dishes. So it is not an interferometric observation that we are
Okay.
considering.
Okay.
It's a single dish. So in this case, would be a combination of many dishes, but smaller dishes. And as far as I understand, for the SKA, you will have not only meerkat, but many other single dishes combined to do this.
Right. Thank you. Do we have a final question from the Google Meet? If not, let's thank the speaker again.
Thank you all. Thank you for the questions.
Bem,
And for
obrigado,
listening.
Camila.
Eu que agradeço. Tchau, tchau.
Acho que... Ah, bom, ok.